Hey everyone, this is Will. Welcome to miniKanren uncourse Hangout 27-ish, something like that. I forget. I've been traveling the last few weeks, and I'm going to be traveling for the next 4 weeks. So this is like a hangout. Actually, yeah, this is the first hangout we've done for a while, right? And then so for the next week, I'm going to be in the Bay Area. I'm going to a summer school at Stanford on SAT and SMT solvers, hoping to apply those techniques to miniKanren. And then for 3 weeks, the 3 weekends after that, I'm going to a synthetic biology summer school at Cold Spring Harbor Lab. Learn about synthetic biology. That's going to be really cool. And then I'll be back for a week, and then I go to Russia. I'm going to be in St. Petersburg, Russia for 2 weeks, teaching a miniKanren course, or a relational programming course. It's a week long. That should be really cool. And then I'm going to be at ICFP in Vancouver, and this game workshop. So it's. I guess we've got one hangout in 5 weekends from now, and then another hangout 4 weekends from now. So yeah, it's gotten a little sparse through the travel, but hopefully it'll settle down after that. Let's see. Last week I gave a talk in Poland on miniKanren, and I'll put a link to that in the video comments. And also I taught a 3.5-hour tutorial on writing interpreters, relational interpreters in miniKanren, and I gave a 5-minute lightning talk that shall remain details shall remain sketchy. But yeah, so I'm back in Salt Lake for a couple days before I head out to learn about SMT solvers. And then before I was in Boston and went to a summer school on program synthesis, which is something we want to do, or starting to play around with in miniKanren. And that was really cool. It was a summer school at MIT, and it had a bunch of people who showed off and taught about their program synthesis tools. So, for example, one tool or one approach is called SysGeis or SysGeis. It's called SysGeis. So SysGeis, hey Igor. SysGeis is it's syntax-directed program synthesis, and so there are tools that use the SysGeis approach. And the idea there is that you have the syntax for language expressed as a grammar, and you use the grammar and restrictions on the grammar to help guide the synthesis problem. And this comes up over and over again in different guises, trying to restrict the syntax of the language so you have a smaller sub-language, and it reduces the branching factor. And then there was also Armando Soler Lozama, who is one of the organizers of the workshop, talked about the SysGeis stuff. That was really cool. Let me turn on my AC for a second. Sorry about that. So that was cool. Let's see. Another thing that was cool was there was another MIT prof who's been doing a lot of work on probabilistic programming. And he showed off all sorts of really cool systems, and I'll have to dig up the links to that. But he showed off 3 or 4 really neat systems, and that stuff is really cool. It's not just program synthesis, but he was doing all sorts of really neat stuff with probabilistic inference. And so he's actually one of the people. I guess he's the head of the venture team. So there's this new language. So he also did, I think, Church. And Nahal, you probably know which professor this is. I'm blanking on the name off the top of my head. Who is running the venture stuff in Church? And first name? Matsinga. Vikash. Vikash Matsinga. I'll put a link in the comments, but he's doing all sorts of really cool work. So there's this language called Church. I might not be pronouncing the right name correctly. But there was a language called Church, which is basically a version of Scheme with probabilistic inference. And Noah Goodman did a lot of the work when he was at MIT there. Now he's at Stanford. And there's this ProbMobs website that talks about probabilistic programming. And Church really, I think, inspired a lot of people to look at probabilistic inference again, probabilistic programming languages, general-purpose probabilistic programming languages that encode probabilistic inference. And then DARPA has this big PAML project now, PPAML, probabilistic programming for advanced machine learning. And a lot of that, I think, was inspired by Church. And there's like a follow-up language at MIT called Venture, and Alexei Radul is also working on that. So there's these really cool languages where you have probabilistic inference. And Rob Zinkoff talked about this in one of the previous Hangouts. So Vikesh talked about this stuff, and he also showed, he did show off the graphics demos. There's some really, really neat demos of probabilistic inference for graphics, and yeah, he showed a whole bunch of cool things at databases, and I'll have to dig up some of the links. I hope some of his videos are online because they're really neat. They're very exciting. Like maybe it's like, hey, I want to kind of dig into this further. So I just haven't had a chance yet since I've been traveling. But the probabilistic inference stuff was really cool. So probabilistic inference is being used for program synthesis. Machine learning is being used for program synthesis. There were talks there. I think the talk that was closest to sort of the things we're interested in miniKanren or doing in miniKanren was, well, obviously we're interested in probabilistic inference, like ProbKanren and all that, but the other thing was there's a new paper out of Penn, University of Pennsylvania, and it's on program synthesis, search-based program synthesis. And all right, let me see if I can read. Yeah, here we go. It's Type and Example Directed Program Synthesis is the name of the paper, and it's by Peter Michael Osera and Steve. I always butcher his last name. Zdansiewicz. Anyway, and I'll put a link in here to the paper. This is an awesome paper, and Steve gave a talk at the workshop, and I thought this is really awesome work. So basically, and I think a lot of the things they're doing actually are things we could probably do in miniKanren. In fact, Michael Ballantyne's already experimented with a little bit of this, but the idea is that they use a type inferencer. They write a type inferencer for a language, and they use the type inferencer. They run the type inferencer backwards, basically, right? Just like we do. And yes, exactly right, Orchid. So they use the type system and the type inferencer to cut down the search space, and you can generate well-typed terms that way. And they combine that with a bunch of other techniques, including, I think they use this grammar restriction and a bunch of other things. But because they're doing type-directed synthesis, they can cut down the search space an awful lot. And anyway, this paper is just full of really cool ideas, and they have very impressive performance numbers. So they can generate list append in what was this, like 3,000th of a second, I think it is. Anyway, they can generate small programs very, very quickly. And but they also have some restrictions. There are some real restrictions on the language they can handle and the types of recursions they can handle and things like that. But it still is a very impressive result. They're using really cool tools. I think a lot of these techniques could be directly applied to miniKanren. And Michael Ballantyne's starting to play around with that, and hopefully he'll join us for a hangout. One of the hangouts coming up relatively near future, and show off some of the synthesis stuff he's been doing. So two of the main ideas we've seen, in this program synthesis summer school. One was restricting the grammar, so you can deal with a small language. And some of the SciGIS stuff seems to be, well, you're synthesizing append, let's say, right? So if you're synthesizing append, you can probably make some guess as to what forms in the language you would need and what forms you might not need. Okay, so if you're doing append, it's dealing with lists. You're probably going to have some list-related primitives and things like that. You're not dealing with numbers in append, so you probably don't need the numeric or arithmetic stuff, right? So that sort of reasoning helps you restrict the language in sub-expressions in different parts of the computation. Now, the disadvantage is you're losing some abstraction, right? Now you have to get into details about what you might have, what forms of language you might need here versus some other part of the program, and it's not always clear exactly how someone is going to tell or know up front what forms would be necessary for the program synthesis. But if you guess right, and they're often very reasonable guesses, then you can speed things up dramatically. So that's one big idea, is restricting the grammars. And we can do that in miniKanren in several ways. A crude way is to take the whole interpreter and to use absento constraints on sub-expressions to say, hey, we don't want you making calls to car in the sub-expression, right? That's pretty slow, and it's a little crude, but that does let you do this, lets you express this a little bit. Another approach would be, okay, well, just write different versions of the interpreter for different parts of the sub-expressions you care about. That's certainly possible, but it's awkward. Another approach, and this is something we've been playing around with more recently, is to change the miniKanren interpreter so that the primitives that are built in, let's say, are all part of an initial environment. So car and coder and things like that, those are in an initial environment instead of being built in with separate rules. So the primitives have their own primitive call form in the relational interpreter, and then you can include in the initial environment all the primitives you care about, and that approach can work nicely. And then the idea there is like you could change the environment to easily change which primitives are available. But I think sort of ultimately a better approach to this is to use something like the grammar constraints that I was working on with Michael Adams, and which we have not yet integrated into miniKanren. The code is on GitHub. If anyone wants to take a crack on it. Basically, I've been waiting till I'm free when Michael Adams is free so we can try to do the integration. I don't think it'd be a big amount of work, like a day or two at most, to integrate it. But that should give you very low-level, fine-grained control over the grammars that are legal at different parts of an expression. And so I think that would be exactly what you want to do some really classy syntax-guided synthesis. So that, I think, would really go a long way towards helping us with program synthesis. So that's one thing, is sort of restricting the grammar of the language. Another trick is, like in Steve's work, is using this type system. So Michael Ballantyne's played that around with that a little bit, having a type system for something like lambda calculus, without polymorphism, but with higher order functions. I think he may have added a fix operator, I forget, for doing recursions. And using that, we have been able now to synthesize append from examples. So we can do a synthesis of the entire append definition from some examples, but it's much slower than the system in this paper, described in this paper. But still, we have that expressive power now. So I think we can push that technique much further, write better type inferencers, use some of these other tricks, like the grammars and things like that, and start doing real whole program synthesis. Maybe you're still talking about something that's relatively small, something like append, but until now we've been mostly focusing on like synthesizing snippets of a program instead of a whole program. So this just should make it fast enough that we can actually handle much larger snippets of code. And then another technique that Steve uses in this paper, that's something that I think that could really help us, and this could also solve other problems, is having normal forms for expressions. So the idea there is, one of the problems with miniKanren's generation of terms, like for say if you're running the interpreter backwards, you want to generate programs that evaluate to I love you, right? So we can do like 1 million of those. I've got 1 million of those programs on my laptop. Most of them are pretty boring, right? Most of them are kind of variants that are very similar to other variants of the programs you'll see. So, for example, say we're doing a number example, right? Say we want to generate programs that evaluate to 6. Let's take that simple example. One answer would be +2, 4, right? So +2, 4 is a program that evaluates to 6. The miniKanren will also generate +4, 2, right? So miniKanren doesn't know that addition is commutative. So things like that, or the associativity properties of addition, so forth. So you can build in knowledge of those properties and knowledge of other properties to help make sure that you only have one normal form for a different type of calculation. So if you want to have an arithmetic expression involving addition that sums to 6, right? In miniKanren, well, you can always have sub-expressions that add 0 to a number, right? So one way to get 6 would be +2, 4. Another way would be to generate +2 +0, 4, right? Or +2 +0 +0 +4 0, things like that. So there are infinitely many expressions, almost all of which are boring. You shouldn't be adding 0 in some sense. If you care about interesting answers, you shouldn't be generating arbitrarily deep trees where you just keep adding 0 to things. That's not interesting. You're going to starve out the interesting answers. So what Steve and his co-author do, I shouldn't call him his co-author. What Steve and Peter Michael do in their paper is they have like a normal form for different types of expressions. So they make sure that you would only have one variant of each of these expressions, right? And that's the only thing that you would end up with. So by doing that, they dramatically cut down on the number of possibilities. And they can also cut off the search in certain cases because they say, well, we've already got this one normal form. This expression that we would consider isn't in a normal form, so we don't have to go down that branch at all. So it's a terrific way of pruning large parts of the search space. So by doing the pruning, or by having normal forms, they can tremendously reduce the search space. So this combination of normal forms for expressions, carefully choosing your grammar, and having types, like those 3 techniques together, they can reduce the search tree like just an unbelievable amount. So that's one of the reasons I think that we can do far better in miniKanren than we have been doing. And I think that all 3 of those techniques are things that we could apply to miniKanren without too much, I think it's more like a method, engineering effort, let me put it that way. I don't think there's like any deep conceptual reason we couldn't apply those techniques. But this paper, which I encourage everyone to read, by Sarah and Zdanowicz. It's a beautiful piece of work. I really like it, and it's probably one of the coolest papers I've read for a while, actually. So anyone who's interested in program synthesis at all, I would highly recommend this paper. And I'll definitely put a link in the chat. And my apologies to Steve for not being able to pronounce his last name. I will figure that out eventually. Zdanowicz. I believe that's the correct pronunciation. Okay. So that was a really cool and inspiring summer school on program synthesis, and I would really like to try to use those 3 techniques with miniKanren. We've been getting better at example guided program synthesis anyway, but I think those 3 techniques will go a long way. And the paper by Peter Michael and Steve have a variety of other techniques that they're also using. But I think those are kind of the ones that give you the most benefit. I believe that's the case. All right. So no analysis. So what would you have to do to implement those sorts of things in miniKanren? What would it look like? Okay. So let's take the first one. The first one is is the grammar restriction, right? So if you like I said, if you want to synthesize appendo or append, if you want to synthesize scheme append, right? You probably don't want to have operators for arithmetic expression, for arithmetic in the language, right? Because that just increases your search space for essentially no reason. So if you can, as a human, sort of reasonably rule out that you'll need those operators, you want to restrict the language. So like I said, you can do it a couple ways. One is you can special case it. You can say, okay, I'm going to have a version of the relational interpreter that's specialized just for this one inference problem. Now that can become trickier because in some cases, because what you might really want is you might even have more knowledge where you say, okay, here's this big expression, and in some subparts of the expression, I know how to restrict the grammar, but the grammars are different in different parts of the sub-expression, right? So then you need more expressive power, and I think that's where the tree automata really come in. You could use absento constraints to some extent, but the sort of a crude approximation would be, let's just start off with an interpreter that has an initial environment that includes the primitives. In fact, I can show that to you. Let me bring up my Emacs, and I'll show you a version of the interpreter that has the code. All right, so here is the shiny new version of the relational interpreter, which I don't think I've shown off. I think this is newer than anything we've seen. So let's look at interp no match. Yeah, so here it is, right here. And so in this version of the relational interpreter, we actually have an explicit initial environment. Normally we start off our calls to the relational interpreter with an empty environment. But here we're actually going to include bindings for the primitives. So car and cooter, for example, you can see that those are tagged with a val tag saying it's a value, and it's a primitive value furthermore. And then this car thing, so internally we still implement car specially, but we have a special relation that's actually going to handle the primitives. So if we look at how we handle the primitives, so we have this eval primo relation, and that's going to check to see the prim ID is if it's cons or car or cooter. So it's still doing the same thing that we'd normally do, but it gives us more flexibility because now we can actually treat cons and car and cooter, for example, just as their own values. So it's like before in the relational interpreter, the way we normally write it, something like car is only, like, you can't treat car as a procedure. In scheme, if I bring up scheme, I can take the car of a pair, but I can also just type car, and I get back the procedure car. Okay, so car is a procedure. In the standard way we've done relational interpreters, however, car is basically a form. It's essentially a special form. I mean, it's not doing any special evaluation of its arguments. It's just doing evaluates each argument, or evaluates this one argument and then takes the car of it. But it's special in that only an application of car to one argument is legal and is recognized by the interpreter. Whereas here, by doing this initial environment, we aren't treating car specially in a sense, and in that a primitive application is just like any other application. You evaluate the arguments in some order, and then we look up this primitive car, and then you apply that thing. And the reason that that's nice is that, first of all, it lets you just type car or put car in a list or whatever, right? You can pull car out of a list and then apply it, that kind of thing. The sorts of things you can do in Scheme. So it gives you more flexibility. But another thing it gives you is the ability to control the environment without really modifying the rest of the interpreter. If you want to, if you want to have a version of the language where car isn't bound, you just change the initial environment and the call to a valid, that kind of thing. So it gives you more control. Another thing that this might help lead towards is something that we haven't been very good with miniKanren. Like, we haven't done anything with modules or anything like that. Okay, so modularity, and I think someone's pointed this out before in one of the Hangouts, that modularity has not been one of the strong points of our relational interpreters or anything like that. So having some sort of module system and controlling namespaces and things like that would be really useful. So going towards this initial environment approach might be a step in that direction. But anyway, once you have something like this initial environment, you can easily control what forms you start out with. If you're trying to synthesize something like append that involves list operators, then you might want to have car, cooter, null, question mark, cons, in your initial environment. You might need other things as well, but you probably don't need plus and times and so forth. So you can control the search space to some extent just by controlling the initial environment. And then you can also probably play, games with absento, saying that, well, if in a certain subpart of the expression you don't want cons to be available, you can do an absento cons. You could do that with the old approach with the interpreter anyway. But so the initial environment, absento, that gives you some power. I do think that the probably the ultimate solution to this problem is to have the tree automata-based grammar constraints. So that's one approach. So that's one way to tackle the grammar problem. As far as tackling, the problem where you're trying to restrict things based on type, one issue that we have right now is that we can't really handle Hindley-Milner style polymorphism in miniKanren very nicely. We can't write a type inferencer for that. We actually thought that we could, or at least I thought we could, but the type inferencer we end up with isn't really doing Hindley-Milner because we need another form of unification called semi-unification to really do it correctly. So there's a restriction of semi-unification that could be used for Hindley-Milner type inference. So that would be another thing to try, would be to extend miniKanren so it could handle the restricted form of semi-unification necessary to do Hindley-Milner and be able to do real polymorphic type inference using that. Or we can just say, well, we'll have a higher order language, but it doesn't really have polymorphism or ML-style polymorphism, which probably kind of suck, but would get us part of the way. And then we could add things like fix, and then we could just restrict the language so it's not polymorphic. And that we can do today, and that's basically what Michael is doing, I believe. David asks, is that really needed for Hindley-Milner? I thought it was just for polymorphic recursion, which ML doesn't have. Well, I might be mistaken. I had a conversation with Michael Adams, and he's convinced that the type inferencers we've been writing that are a handling of polymorphism isn't correct in the following way. It seems like the programs that we type check with our type inferencer might be the same problems I would type check under Hindley-Milner, but the types that we're getting back from the type inferencer are not the correct types that you would get in the Hindley-Milner type inferencer. So it's like if we only wanted to type check and say whether or not it's valid, maybe we'd be able to get away with the current approach. But if we actually want to know what the type is, then he's convinced our approach is wrong, and basically he's convinced me too at this point. But that'd be a good thing to explore to talk about that a little bit. Maybe he'd be willing to talk about it, or I know Michael Ballantyne has looked at this problem quite a bit. But basically, Michael Adams has a problem. It's like, okay, type in, infer the type of this, and when we do it, we come up with a type that's apparently not correct. So it's kind of this weird thing. Like, it might actually be that we're type checking everything correctly, but we can't infer the type. it's a little yucky, but the semi-unification is very interesting anyway, and it might be that there are other problems that we could benefit from. So anyway, that'd be something to play around with. Anyway, so having classier type inferencers would be nice. Even just with inferencers for maybe restricted languages that aren't polymorphic, I think we could still push much further the interaction of the type inferencer and the interpreter. So one thing you want to avoid is, because the way conjunction works in miniKanren, if you're not careful, if you have a type inference phase and then followed by the interpreter phase, and they're two separate relations, then the type inferencer can end up completely dominating the search. And that's not what you want. What you really want is for the type inferencer and the interpreter to be able to kind of interact with each other in a way to help prune the search as much as possible. So that's something that Michael Ballantyne's been playing around with, but that's something I think could be pushed a lot further. So that's something that perhaps he could come on and show off with the type inference he was doing for Appendo, or for Append, I mean. And then the last one, having the normal forms. Yeah, I don't know. I haven't thought about that too much. I guess once again that might come into grammar restrictions to some extent. That kind of feels like a grammar type thing. Or we could have restrictions like if you do an addition, say you have plus, if you've got an expression that involves plus, that you're not allowed to have a 0 in one of the arguments, or the 0 can only appear on one side, or the smaller number has to appear on one side, on the left side, or something like that. Now you lose some power and some expressiveness when you do this, right? But you can remove lots of nonsense answers at all, or you can have a little bit of a trade-off. You could say, well, you're allowed to have 1 0 in the expression, that kind of thing, and that's the sort of restrictions that that you see in the paper by Peter, Michael, and Steve, is that they'll have restrictions on, they'll say, hey, in this sub-expression, the number 5 has to appear, or something like that. And then as the sub-expression gets more and more ground, as at some point, if they've reached their search depth or whatever, then they'll have to put a 5 there. So they use that technique also to try to make sure that the search sort of bounds on the search depth also interact with the grammars and the restrictions on the special form, on the normal forms, and all those sorts of things. Yeah, I think Nahal is sort of like that, as like a grammar or rewrite rule or some sort of restriction. You can think of it as a simplification rule, maybe. So basically, you want to make sure that the expressions you're generating have already been simplified in the ways you care about. I think that's sort of the way to think about it. You don't want to spend a lot of effort generating terms that are either essentially logical duplicates of other terms or that are boring. So for example, miniKanren loves to generate things like an application of lambda x with the body of 5 to some other thing, where it's like not using the variables involved in the lambda. So that's kind of stupid. It's like, why would you introduce a lambda and not use the variable, right? I mean, it's just pointless. No one would actually write that unless they're trying to prevent divergence or something like that. But you don't really want those answers, and certainly you don't want like 1 million of those answers or 1 billion of those answers. So you want to try to get rid of those answers or restrict how many of them there are. So that's one thing we could do, is like, okay, if you're ever introducing an application, you have a lambda, you better use that x inside the body in like an interesting way. So by essentially restricting the grammar to have special normal forms, you can get also more pruning and eliminate lots of boring answers. So that's another thing that would be interesting to play around with. And I don't know how much detail this paper goes into. I actually haven't read the paper yet. I saw the talk, that was great, and I saw the demo, which was great. And Michael Valentine read the paper and really enjoyed it, but I haven't looked at the details yet, so I don't know how much they go into details of the normal forms. I think some of the SIGA stuff also has this concept of a normal form. But anyway, these are all sort of restrictions on the grammar, in a sense, or restrictions on what your terms can look like to prune the search tree, and that so Steve showed some slides where he showed the size of the search tree down to a certain depth, and just by having the normal form, it vastly reduces the search tree, and having the type system layered on top vastly reduces the search tree. So it was like 1/10 of 1% or less than that, with some of these changes. For a search tree that wasn't super deep, but that was deep enough to be of interest. So that's the sort of thing that could speed up our system by orders of magnitude for synthesis problems. Okay, Orchid, you have an MK challenge. All right, what's your challenge? Okay, what is this? Is it a Quine-related thing? Ooh. All right, let me screen share. Quine.zip. Below are two text boxes. The one on the left is for input. The one on the right displays output. The goal here is to write a series of commands on the left that results in output matching exactly what's on the left. Okay. In the world of programming, such a series of commands is called a quine. Commands available to you are print m. Prints the following m lines of input. Any command that is printed will not be run as an action. Repeat mn repeats the last m lines of output, starting n lines from the end. In both commands, m and n are natural numbers. Okay, so let's see. We got print 2, print 3, print 4. Repeat 1, 1. All right, how's this work? Prints the font. Okay, so let me just try one. Like print 5. What does this do? How do you run it? I'm doing something wrong? Help! How do I actually make like output appear? Print 1, print 1. All right. All right, help me. After print 5. Oh, whoa, what the? It only works on the other input and output. It doesn't do anything itself. Okay, so, all right. Print m prints the following m lines of input. Okay, so any command that is printed will not be run as an action. Okay, so the print 5 is printing the next 5 lines. Is that right? So if I do print 2 or print 17. Oh, now I get it. Now I get it. Okay. Okay. Right. So it doesn't print 1 or print 17. Okay. I see. And then repeat mn repeats the last m lines of output. So that's going to repeat what's here, starting in lines from the end.
Hey guys.
Oh, I need a unicorn chaser. All right. Okay. So, yeah, I'll tell you what. I will. Let me give. Uh, David. Sure, controls is the U. And Orchid. Feel free to ban any trolls. Okay, so let's see here. We've got. We want to do a repeat now, right? So let's see. So how does repeat work? Repeats the last m lines of output starting n lines from the end. So if I'm going to repeat like 2 starting 1 line from the end. Whoa. What? So you can add more. Repeat to 1.
You've got the print 5 as the first thing, right? So it's going to take 5 lines.
Oh, okay. So let's see. So if I do like print 2, well, okay. All right. So help me out. I'm a noob here. So print 2 is going to print what, these two?
Yes.
Okay. And then repeat to 1 is going to take the output. It's going to take. Is there a print 2 0? Does that work? Would that print the 1? No, it has to be 1. Oh. Okay. Print. Okay, print. I'm kind of getting it. All right. Okay, so your challenge, Orchid, is to be able to solve this problem, right? So we get a coin back. So I guess what we would have to do is write like a little interpreter, right? Or write a little system that handles this, and it's going to have to know about the output. All right. So input, okay. Based on the LZ77 decompression scheme. Okay. So Orchid, have you actually tried this yet? I tried it, but I made a slight mistake in my interpreter. Okay. Did you want to try debugging it or looking at it? I don't think I fully understand the rules of this, but right? Let's see. I think other people do. I have to rewrite, but I can't program that. Oh, okay. So that is a nice challenge. That's a nice challenge. I'll put this up on the comments. So this seems like exactly the sort of thing you could do in miniKanren, right? I think it'd be a difficult one. Yeah, it. Seems like it might be a difficult one. I wonder if you could do stuff like that, would that do anything interesting with in terms of compression, decompression, things like that? You know, would you be able to do other problems? Yes, you'd be able to make a zip file which decompresses it to itself if you solve this. Oh, well, that seems like a worthy problem. So it's like a zip file client, right? Yeah. Okay. Well, that is a worthy challenge. I like that. I will have to give that. Yeah, I think you're right. I think this is like kind of a little tricky. So I think I have to look at it a little more closely to try to make sure I understand the rules of the language. But so I guess the weird part is so you have an input and you have an output, but the input commands have to do with the output, right? That's like kind of a little weird. Well, maybe they don't have to do with the output in some sense. I'm sure you could like model that in some nice way, but you know, if you thread through the output monadically or something like that, then you'd always have access to the output. Well, maybe that actually wouldn't be too hard to model. That might be fine. Yeah. Okay. Well, that is a worthy challenge. I think that's really cool, and I encourage everyone to try to play with this one. I'm looking forward to having like a little time to sit down and just hack on a cool miniKanren puzzle and not be running to an airplane or working on a paper. But this is yeah, I like the ability to do a quine a zip file quine using this. I think that'd be neat. Well, thank you. That's really cool. All right. So, oh yeah. So I was going to show. I was going to show a problem that we noticed recently. Michael Valentine and I were playing around, and we kind of ran into this issue. And I think this is like deeply connected to miniKanren search and to how synthesis works or doesn't work well in miniKanren. And I think gets it to the heart of what we would need to change or be able to express in the search, and if we want to make the synthesis in miniKanren much more efficient. So let's see if I can show you an example of that, of what's going on. And then also Nahal, I think, hopefully, is going to show us some Julia stuff. Actually, how are you doing for time, Nahal? I know sometimes you got to run. Did you want to show us the Julia stuff now? I'm not sure if Nahal has his ears on. All right. Well, I will go ahead and do the screen sharing then. All right. Let me try to show you the problem that we ran into. Let's try doing some synthesis. Let's pick, say, interp no match. Actually, let's do the test all. Actually, let's do this one. Okay. And now let's look at the code here. And let's, okay, so this is a good example, I think. I think we can do something like rumber. Well, actually, we can probably just do, let's just try doing append. Since we all know append quite well, I think. All right, so here we're trying to do some program synthesis. Actually, let me just start out, make it simple. Okay. So here, try running this forward. That's fine. So this is append running in our relational interpreter of LLL. So we're running essentially the scheme code inside a LUTREC definition of append. We have a call to append with 2 arguments, right? And if we put the query variable from our run right here, this is effectively running append forward. And we can see that sure enough, we get the result of appending the two lists A, B, C, D, E, right? And if we put logic variable inside the call to append, now we're basically running append backwards. And I've pointed out, before the Hangouts, things like that, that we can actually generate arbitrary expressions in the interpreter's language that evaluates the list ABC, right? And if we want to put a quote here, we put a quote, then it says actually has to be quoted data like a list, and then we only have one answer, ABC. Okay, so those are the sorts of games we can play once we have this relational interpreter. But another thing we can do is try to do some code synthesis. So here we've got S, which represents like one of the list arguments, and so this is part of the code for append, and we can actually replace the S with a logic variable, and we get back an S. Okay, so we're doing some code synthesis here. And we can replace like carvel, put that there, and we get back carvel. Okay, so we can do that. And you might think that we could go inside the null of L, so we can do that a little bit. Let's put a Q there so we can get back to the null. Yeah. Okay. But if I replace that entire null of L expression, like basically this doesn't come back, or at least doesn't come back right away. Compare this to the code synthesis paper I was talking about earlier, where they can synthesize append in like the whole definition of append in 3,000ths of a second, right? Oh, well, actually, it did come back. Oh, okay, well, that's cool. But it's not nearly as fast as you would like, or at least as fast as I would like. So it does come back, but it took a while. And as we have bigger and bigger sub-expressions that we want to synthesize, the running time increases exponentially. So it took us a while to produce that little snippet of code, but if I also, if I tried to do, say this whole append recursive call or whatever, I mean, who knows? That might take minutes, it might take hours, it might not come back before it ran out of memory. Okay, so why did it take so long to produce equal ? L of quote empty list? It might seem like that's not such an annoying, or not such a difficult thing to generate. Okay. So I was just curious why that was taking so long. So we can actually change this a little bit. So instead of saying the output is that particular list, let's just say that the output is something that we don't care about. We're just ignoring the output. Okay. I'll introduce a fresh variable for ignore. We don't actually care what the output is. That means that we're allowed to generate any value we want for Q, any code snippet at all for Q, and we'll consider that legal. Okay, and we're just going to try to look at what sort of values are being generated, what sort of expressions are being generated. Okay, so we got a number and all that. Well, let's just try generating like 100 expressions. Okay. Now look at this. So what we're doing is we're generating 100 expressions, 100 scheme expressions, according to a relational schema interpreter, within the context of this letrec definition. Okay. So we're in the context of the if, inside the lambda, inside the append, inside the letrec. Okay. And if you look at the sorts of answers we're generating, these aren't just sort of randomly distributed or uniformly distributed lambda expression or schema expressions in some sense. It's not, we're not getting a nice mixture of cons and cars and coulders and all that. We're seeing that the search is almost completely dominated by these stupid lambdas. And let's pick one down below and just show how ridiculous it is. Okay, so here's the lambda expression that we just generated. Let's take a look at it. Okay. So what we generated, or what miniKanren generated, was a lambda expression with 46 variables, or 46 formal parameters, right? It'd be like lambda of x1, x2, blah, 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 to x46. And then the result inside is like something totally different, which is, what is it, the symbol or something? Where is 46? Oh, it's some arbitrary thing? I don't even know what it is. I guess it's an arbitrary expression. No. Anyway, but this is ridiculous, right? No one, maybe computer-generated code would have 46 arguments, but no normal lambda you would ever write by hand would have 46 arguments. So it's just, what's happening is the search, for whatever reason, is just creating bigger and bigger lambdas, bigger and bigger lists of parameters for the lambdas. Okay, so that's why, and you can see, like, as this goes on, it's like 90% or 95%, maybe more, of all the answers are these stupid lambdas. So miniKanren is spending all of its time essentially generating these ridiculous lambdas. Now compare this with what happens if I don't run, if I don't put Q inside the context of that giant expression. What do 100 values look like then? Still not so good, actually. Still not so good. Better. It's better. Get some LetRecs, some lists, conses, and things like that. It's still not so great, actually. And part of this may be the way that we put the primitives, the prim expos, handling the primitive applications. Maybe that's part of the issue, but it's still, well, actually, we still got up to 40, 47. This is actually even worse. It's even worse. Wow. Sorry. Okay, so that's pretty bad. That's pretty bad. That's pretty bad. However, okay. So here's I think maybe the insightful thing. All right, so let's try one more test. Let's try one more test. Yeah, that was pretty grim anyway. Okay, so we've got. Let's just try this. There's one other example. I was trying to think. I was trying to remember how this works. So I think what I was trying to do was to sort of synthesize things like the "I love you." Right. So those, we could. If I do like 100 of those, let's see how that looks. Yeah, a lot of these are still kind of stupid, right? So this is, I think this is showing why you want to have some of the normal form stuff, or you want to try to prevent answers that are just ridiculous, like where you have this argument that's never being used in the body, and therefore the expressions can just kind of grow arbitrarily large. And all of these answers here are essentially the same. They're all essentially the same. They're just, you have some argument, you don't care what it is, and then you just return the list "I love you." And it really doesn't matter so much what these values are on the outside. They're all equally boring because the whole thing was boring to begin with. We want to get rid of those. But okay, so we can affix at least at least the good news is we can generate these quickly. I mean, they're all pretty boring, but we can generate them pretty quickly. Like I think I can do 1,000 of them. Yeah, it's like that's that's relatively fast. But if I go back to the context of the lat rack, well, let me just see if I can. See if this. Yeah, maybe it's just as good. Well, I'll have to talk to Michael about that again. I forget exactly the example I had, but I guess one thing that's very clear is that we're like almost all the answers are dominated by these stupid lambdas, where the number of arguments is just growing essentially without bound, right? That's like about the most boring thing you can imagine. So I think trying to restrict the way the terms can look could help with that a lot. Or also having some metric on the size of the term, like having some penalty or modifying the search so that terms that are bigger, get penalized. That's another thing that a lot of these synthesis systems do. They put some sort of measure on term size. So for each additional argument to a lambda, you might want to increase the cost, maybe even non-linearly. I don't know. Try to keep the number of arguments down. Okay, so Orchid asks, what is the ultimate goal of program synthesis? The ultimate goal of program synthesis, I guess, is automatic programming, where you can just give a specification to the computer, and have it generate the code for you, right? No one really knows how to do this. Can do it for some certain very restricted types of programs. But I guess one example is, well, if you write a bunch of tests currently, as part of test-driven development or something like that, well, why can't you use those input-output test examples to actually synthesize the program, right? Any set of tests isn't going to give you a complete specification of a program in general, but it could help a lot. And if you knew other things like type information, right, you could probably fill in much of the detail. It's very expensive to do this, and it's can be awkward to express. But so I think what people really want to do is they want to have something where they can maybe partly write down some formal specification, partly write down a bunch of tests with input and output examples, maybe do something like restrict the grammar a little bit, and then have the system come up with the code, or at least come up with sort of reasonable programs. And one, a lot of these systems, they'll try synthesizing a program, and if that program isn't correct, then what you have to do is you enter a new program input and output that shows why that program snippet isn't correct. And then the system will go back and, from what it's learned, try to synthesize something else. So there are sort of these Oracle guided searches where an Oracle could be a human, it could be another test, another program, or another implementation, or whatever. Okay, can you do absento quote lambda q? There needs to be a way to make miniKanren uninterested in pointless terms. Yes. Yes, 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 yes. Okay, so I like this idea, Orchid. All right, so we got all these boring answers. Let me just do like 100 instead of 1,000. All right, what happens if we do absento quote lambda and q? Huh. That looks a lot more interesting to me. Wow, that's a dramatic change. Okay, so here it is without the lambdas. We get cons and ifs and ands and ors all over the place.
Can you share your screen?
Oh! Yeah. Don't want to see a picture of that guy again. Okay, there we go. All right, Orchid. Let's go back. So here, above, this is what we get from the run 100 before. So here was a query. So we're just evaluating arbitrary expressions that should give us back the list I love you. Okay, so the first one is quote I love you, and then almost immediately afterwards, it just becomes like dominated by these lambdas that have the body I love you, right? And it's like almost a huge percentage of these answers are just variants on that. Not very interesting. But if we use Orchid's suggestion and we use Absento to say that lambda can appear in Q, then the answers become more interesting, or at least at first glance they become more interesting. So we've got all these primitives being used and so forth. So I wonder, all right, let's go back and try that synthesis example that took a while, right? So I replaced, I want to make sure I'm doing it right. So I think this was null of L. Okay, cool. So let's try this synthesis problem again. And let's time it. All right, so my theory here is that almost all of these expressions being tried involve these stupid lambdas all over the place, right? They've got nothing to do with anything. So, I don't know. All right, so it took 15 seconds. 15 seconds, okay. So let's try Orchid's suggestion. Let's do an Absento lambda on Q. .5 seconds. Okay, so that's an order of magnitude faster, even though the Absento constraint is actually quite slow. So another way we could do it is actually, well, so the interesting thing is like we can't actually remove lambda from the grammar of the language, right? Because we're using lambda. It's actually used in the definition of append. So this is an example of where you want in a sub-expression a different grammar than the grammar for the entire language, right? In this particular sub-expression, we don't want a lambda to appear. And then, there are probably other ways we could restrict it also. But this is a lot of the sysguy stuff, or SIGA stuff, is saying in this particular part of the program, we want a different grammar. Okay. Also, obviously, things like types could help, so forth. You say, hey, if this is an if, this really should give you a Boolean. This should be a Boolean expression here, right? So a type inferencer could help with that also, and help prune it. But that change alone already gave it an order of magnitude speed up. So that was pretty sweet. Yeah, Eric, you said something like property-based testing could be useful there, I guess. That's right. I mean, I think part of the idea of the example-based synthesis is the idea that the example-based synthesis and things like property-based testing, and also just fuzz testing and just standard test-driven development, they're all related in a way, right? And if you have to write down these tests anyway to test your code, you might as well use the tests or generate the tests. So if you had property-based testing, that could fit in. So what we would like to be able to do is combine property-based testing with the example-based synthesis and the relational interpreters, because in property-based testing, you're writing down part of the semantics of the program. But generally, it doesn't really know, these tests and the property-based testing framework doesn't really know about the semantics of the programming language necessarily. Whereas in our system, once we have an interpreter for the language, it actually knows the semantics of the language. So it feels like you should be able to do something. I think Matt might call this like semantics-aware property-based testing or something like that. So hopefully you could do something as sort of like a hybrid approach. But thank you for that suggestion, Orchid. That sped it up in order of magnitude. So I think if we can do things like restrict the grammars in different ways, that this could have have a big impact on what we're doing. There may be other forms that we could also restrict other than lambda in that case. I don't know. Let's see if we looked at the interpreter. What else? So we had a letrec form too, I think. And there are a bunch of other stuff, but like there's lambda and a letrec. Yeah, so there's a letrec form also. Like probably letrec shouldn't be a test, appearing in test position in that if. So we could potentially also restrict it. I guess the letrec always has a lambda, so that's maybe not such a big win in this case. Okay, so my guess is that the letrec's not really going to help because our letrecs always require lambdas. Yeah, so that's it's about the same speed. I don't know if it makes a difference if you reorder those. Yeah, it's about the same. Okay, so the lambda, so the letrec part subsumed by lambda. But there may be other things in the interpreter or in that language supported by the interpreter which we also don't really need, and that might speed it up even more. So that's one thing you could do is restrict the grammar. But another thing is that, well, okay, what I wanted to try to show also, unfortunately, I didn't show that, and Orchid pointed out the nice way to write this. The other thing I wanted to show is that we've encountered cases now where it seems like, depending on the context of where you put the logic variable, the generation of the terms seems to differ significantly. And once you start putting these logic variables deeply inside of the code for append or something like that, you're losing some of the ability to run backwards, or you're entering more of a generate and test mode. Let me put it that way. You're entering more of a generate and test mode than you would otherwise hope to be. Like when you're running something like a Quine, or if you're running something like the I love you programs just directly, it doesn't seem to take as long. Actually, that's one thing. Let's try that one. I don't remember his screen share, but that's a fun one. And that one definitely ran slower. So let's see if we can use Orchid's trick. Speed this up. So one thing that is fun is that you can do things like generate the I love you inside the context of append. So let's see if this works. So what we want to do, let me get rid of the absento first. We want to generate expression Q that evaluates I love you, but it's in the body. We're putting the variable in the body letrec, right? So it's allowed to use the lambda we just defined. Okay, so let's just try doing let's see how many we can do. Like 10 is pretty fast. Okay, cool. 100 is pretty fast, hopefully. Yeah, okay, so that's pretty cool. You can see it's kind of boring stuff. Okay. All right, let me try doing something a little harder. How about a Quine in the context of append? So now we can have a Quine that uses append number. Okay. I think the fourth one's the Quine. Well, I guess a Quine uses lambda, doesn't it? So that's not going to work. But if we just see, let's see how long it takes to do a Quine normally. Oops. Okay, the fourth one's the first real Quine. Okay, so it took 2.8 seconds to give us the first real Quine. All right, if we do it here, how long does it take? I think it takes way, way longer. Oh, huh? Okay, I'm being dumb. There we go, that's better. All right, That actually went that much longer. 4.8 versus 2.8. Yeah, not that bad, I guess. Not that bad, I guess. And we could do. So how long does it take to do like 100? Thousand, 10,000. Okay. 5.4, and let's compare that to just having it outside the LUTREC, or outside the append. How much overhead is there in that append? Wow, those are actually almost the same. Okay. Well, I think there are two lessons to be drawn from this. One is that ORCID's trick is quite nice in reducing the search space when you strongly suspect there's not a lambda to be made there or to be used there. And the other is I don't really know what I'm talking about when it comes to the speed of some of these examples. I think we had to play around with this a little more, but the append trick actually worked really well. So I think that's, having more formal ways to represent things like that, having things like the tree automata-based grammar constraints should go a long way towards making that easily expressible. And the absento actually works okay in that case. It works okay, and it sped things up a factor of 10, so that's pretty good. I don't know. I think I guess the bottom line is we don't have a very good intuition as to why some problems take a long time or what's really going on in the search. It's like it was a little bit of a surprise to see how many of those terms were just like these lambdas with increasingly large number of arguments that were just ignored, right? So I think two of the big problems right now in miniKanrens, one is like we don't have a very good way to talk about or formally reason about or quantify the answers we get back from the search. And the other thing is, we don't. Well, that's one problem. What's the other problem? The other problem was. I don't remember what I was going to say, but basically, our understanding of exactly what's going on with the search isn't so great, and so when we're trying to do one of these synthesis problems, I guess here's the thing: we don't have a good model of. Actually, let me screen share again for a second. Here's like what we can't reason about very well right now. So stuff like if I want to do a program synthesis problem here. If I go back to like a previous version, where we have an example. So here we're doing example-based synthesis, right? And what I don't have a good sense of is the relative time it takes to synthesize things. Like, okay, so that null of L, that's an expression that basically it's an application, a null, and L. Okay, so it's maybe has a size 3 if you want to think of it that way. This car of L also has a size 3. So if I replace that with Q, okay, so that comes back much faster. It's like 12 milliseconds, right? So the car part, that's fine. That's pretty fast. That's faster than the null test. Why is it faster than the null test? What about this coder? What if I remove that? How long does that take? Well, this is much slower. For whatever reason, removing that coder is much more expensive than removing the car, right? And I don't know why that is. Why would removing that? I mean, it's inside a recursive call, so maybe that's part of it. But why is that so expensive compared to removing the car part? those terms are of the same complexity or the same size, right? Maybe what needs to happen is, in order to make that one work, we need to do something like have a list of examples, right? So this is another thing we've been starting to get into is, well, what happens when we have multiple calls? So like you could have like a base case, and then you could have a list of multiple answers. Oops. No, that's going to be quote. Let's say this is like FG. Okay, so now what you can do is, we can play around with multiple calls, multiple tests. So we got 2 tests, calls, and then the expected outputs for those. Okay, and that should work. Yep. All right. So now if I remove the car of L, hopefully that's still fast. That is. And now if I go back and take out the coder of L, is that any faster? Or does that second test help any? I don't know. I mean, it's definitely taking longer than the car one. If I go back and put a variable Q there, how fast is that? 42 milliseconds. Okay, not super fast, but not ridiculously slow. If I say X and Y, and I replace, and I say it has to be a call, but we have X and Y, which are unknown. Give it a little bit of a structure, and let's do Q fresh XY. Equal Q list XY. There's just a way to give a little more structure to the synthesis problem. So how does this do in terms of running time? This is pretty bad. Yeah, it's like really slow. So if I go in there and if I give it a hint, if I say that X is coder, then it comes back right away. But if I remove that test, and even though I'm not synthesizing that much, it's gotten really, really slow. And why is that so slow versus removing the car of L is fast, removing the null of L is slower than the car of L, and removing the coder of L here is way, way slower than either one. Okay, so I don't have any sort of theory or way to easily reason about that. To reason about what is the search doing, how can you try to figure out which of these synthesis problems will be expensive and which will be less expensive, right? I mean, it's largely trial and error and just kind of guessing, and I can kind of have a little bit of intuition about what's going to be expensive, but my intuition is really bad. So that's something I think we're missing. We're missing a way to reason about that. Nahal asks, is there some sort of tool we could create to visualize better what is going on? Create a tool. Yes. So a couple of people have tried to create tools for visualizing miniKanren search. I guess part of it's I don't know exactly what the tool should display. What would be the useful thing to see? I don't know. But I guess the other part of it is, maybe in addition to the tool, what it's really is saying is that there's something kind of broken with the way our search works, and that the information isn't flowing forward and backwards well. Because that's the other part of this. I mean, it's there should be some contextual awareness of kind of what's going on. I think part of the problem right now is that with that particular example, in a sense, miniKanren search is running it forward. It's not taking advantage of the fact that we have both the input and the output to the call as well as you'd like it to. Yeah, more like high-level conceptual thinking than just searching. Yeah, so that's the question, right? This is like, what can we do for search? I mean, if you look at this example, what do we have that's instantiated? You know, we've got basically everything in all the code is instantiated except for X and Y, and X and Y already are, you know, there already is a lot of structure here, right? There's a lot of structure here. You've got example calls, you've got example outputs. We know all the code for the interpreter. We've got almost all the code for append, right? We know that it doesn't involve a rec or a lambda in these expressions. You know, that is an awful lot of information, and it feels like our system should be able to take these example inputs and outputs and kind of flow the information down and maybe up in some cases, and try to, you know, try to constrain the search so that when we're searching for X and Y's, we're not doing sort of blind generating tests, but that we have a little more contextual information. Now the types could help a lot there with giving some more context, but it's like it's kind of infuriating that, you know, there's all this contextual information. I think in our current search, it's just not being used as well as it could be, and I think a lot of that has to do with our implementation of conjunction. Has anyone been able to write programs which do that? Well, I mean, I guess it depends on what you mean by doing that. I mean, things like the type systems, right? That has some level, that's additional level of reasoning, and that can help. There are heuristics that people use for search. There's, you know, things like restricting grammars and all that, and so a lot of that is pushed onto the human, obviously, and maybe some of that would be okay to push it onto the human. Maybe that's okay. I mean, so one thing we can do, which, you know, to be fair, would, well, it feels like a little bit like cheating, but if we really want to make the synthesis problem run fast, then, you know, basically the real way to make this run fast is to put symbolo constraints on X and Y. I think that would make it come back essentially immediately. Yeah. But of course, that's, you know, kind of cheating. But, you know, you could have heuristics that would say something like, you know, well, first of all, from a type standpoint, you know that this has to be a list. This expression has to give you a list, right? So that already, just having that type information would really help. Also, there's heuristics for writing recursive programs, right? So like, if you ask a question about an argument like null, first of all, you now know that L is going to be a pair or a list or whatever, right? It's going to be a list, probably proper list, and you also know that in recursion, in order to hit the base case, you have to get that list closer to the empty case, right? That's what a human does to reason about things. So probably you're going to be taking something like the coder of the list, right? So you know, just as a human knows or can learn these rules, you know, we could somehow teach that to the system. Or another rule that you often have is that if you don't ask a question about an argument, like S in this case, usually you just leave the argument alone, right? So there's knowledge that we teach every undergraduate at, you know, who learns Scheme about how to write these sorts of programs. Or like that book, How to Design Programs, is basically this, right? The types plus a bunch of heuristics, design methodology for writing little recursive relations. And it feels like we should be able to encode that information somehow. So I guess that's the question. Like, how could we encode a rule like the fact that, you know, if you ask a question about an argument, then when you recur on it, you have to get, you know, then when you recur on it, you're going to change it, right? And furthermore, you have to get closer to the base case. Maybe you could do some machine learning, maybe probabilistic inference and all that stuff would help, or maybe encode it more like a heuristic. I don't know. I'm not sure what the right way to do that is, but basically, you probably want to give some preference to which of these choices you're choosing, right? It's like if you told me that you're writing a little recursive relation and that you didn't check and you didn't ask any questions about the second argument, and you're going to make a recursion, I would tell you immediately, probably you're not going to change that argument in recursion, right? So, there are like maybe 10 rules like this, 10 rules of thumb that are inexact, but they turn out that they work almost all the time. And it seems like you could do pretty well with that. I'm not sure. But anyway, so those are the synthesis things I've been thinking about, and as you can probably tell, I don't have like a super detailed understanding of kind of why things aren't working well. But yes, so I think some sort of tool would be great. All right, Nahal, you had a question.
Yeah, I did have a question. So I'm trying to think of, like, what I see here feels similar to sometimes what happens in math, where, so right now we have this relational interpreter, and it can pretty much do anything. And that's great, and it's also a source of problems, right? And then, if this happens in math, usually everything's at the level of polynomials. You can do everything with polynomials, and then you realize, okay, that's just way too much generality. And then finally someone slaps an algebra, which feels very similar to the kinds of stuff you're doing before, but it restricts the domain, and then you can make progress. So it seems like one way of doing this kind of synthesis would be the following workflow, where you, let's say, write a relational interpreter, and then in that language, let's say scheme, right, we write for our particular problem domain, like 4 or 5 functions that we think as humans are going to be useful, right? So if it was list processing, it might be full del or map or whatever. But if it's numerical stuff, maybe fast Fourier transform, whatever, there'd be like a set of 4 or 5 functions. And then there's sort of like 2 levels of sophistication of how you might do synthesis. I'm curious. I don't understand how I could do this in miniKanren. That's my question. But the idea would be that, let's say I write these 4 or 5 functions. Now, what I want miniKanren to do is, let's say I give it a bunch of examples of, like, here's the input and here's the output to my program. Here's the input, output, etc. And now create a program that uses only these 4 or 5 functions, and let's say no recursion. But it could be arbitrary long expressions. Try to create this. Create a function that calculates that thing. Like that, I feel, is essentially the essence of what happens when math starts using algebras to simplify the search space. And then, you can think of that. So I don't know how you'd express that in miniKanren, where, you start with a relational interpreter, and then you add a few extra functions, but you say, please generate a program, but use only these functions. It seems certainly doable. It's a little bit different than absento. It's like, use only O, right? So that's one issue.
I think that's basically what these tools are trying to do, right? The ones I was talking about, in that you're restricting the grammar somehow.
Exactly. Yep.
Or you could have a normal form, and a lot of the tools try to remove recursion, or they only allow recursion through things like fold, right? Yep. And then another heuristic that a lot of systems use are things like always give preference to the smallest answer, and then things like the normal forms, right? And maybe that feels a little like an algebra, but yeah, I think that's right.
So normal forms. So that's the other point I wanted to ask about, is that when I think of normal forms, I think of normal forms as actually computation, which is slightly different than algebra, right? So there's 2 ways of doing things. You can either just take an expression and use a kind of set of rules and brute force calculate something down to a normal form, That's one way of thinking about it. So you could have a bunch of matrix expressions, you just kind of crunch through it. At the end, you have a matrix, and you compare the two matrices to see if they're similar or the same. That's one way of expressing computations, and it's quite beautiful because it just always works. The other way is you have rewrite rules, right? So you know that there's a bunch of shortcuts that you can take to simplify the calculation that you're doing. But it's just not clear how you use those rules every time you do a calculation, right? So in a normal form, you just have one algorithm that takes you directly to an answer. It may not be the best way to do it every time, but the alternative is you have these rewrite rules that let you simplify an expression and let you defer doing kind of brute force computation until you're kind of towards the end. And that's the thing I can't figure out. Like I really would love one day to try to work through a miniKanren example where we try to explore those ideas. It's just not clear to me exactly how you do it.
Yeah, so maybe normal form is not even the right term. Maybe I should call it restricted form or something like that. Because I think what they're trying to do, like with the Saiga stuff, is they're taking observations of properties of their language, things like addition is commutative and associative, right? And they're actually essentially encoding that in a grammar, so that you don't actually have legal terms. That are that like you actually can't construct terms that don't follow this formula or don't have this shape, right? So like they'll have a restriction like, okay, you're allowed to add two numbers, let's say, but you're never allowed to have the smaller number on the right of the addition, things like that. And like they'll just say like that's just like grammatically incorrect in our grammar. Okay, we're just going to restrict the grammar so you can't even express it. Not even like so you don't have to worry about normalizing it. Like anything that violates this, where you'd have the smaller number, to the right or whatever. Like we're just going to say that's not even legal, and you can't generate, you can't even express it in the language. So that restricts the expressiveness in some ways, but it can dramatically reduce the search space, and it can avoid having boring answers. Or you can, I think that they had some restrictions with zeros. So things like, if you have an arithmetic term, either the whole term is 0, or if that arithmetic term contains a multiplication, neither of the subterms can be 0. It can never have any 0 inside of it. That would give you a 0 for the entire computation, because like, hey, if you want 0, we're just going to represent it as 0. That's it. So as soon as you know there's a multiplication, you know that both subterms are going to give you something that's non-zero. So they're really restricting the language, and in some ways you lose a lot of expressiveness. But in terms of generating interesting answers, it actually seems like a pretty reasonable approach. Some of the examples that we show in miniKanren, well, here's a million ways to generate 5 or something like that. These systems would reject that and say, no, there aren't a million ways to generate 5. Almost all of the ways that you're generating, or maybe there are a million ways to do it, but almost all the ways you're doing it are either boring or redundant, and we reject 99.9% of the answers you generate, stuff like that. So I think they're trying to express it sort of at a grammatical level, where you just have such a restricted grammar that you can't even express things that aren't in this very restricted form. Does that make sense? And it feels a little different from the rewrite stuff.
Yeah, that makes sense. I guess the thing is that, and I see this happening in math too. Like if you look at the history of math, like you start with rewrite rules that seem reasonable, like let's just always put the smaller number at the beginning of the plus expression, right? But somehow, it takes a lot of wisdom to get the right set of rules. Like that rule probably isn't the best rule.
Yeah.
And so these mathematicians, they spend, that's what they do actually, so try to figure out what are actually the rules that are going to give you the biggest bang for buck. So so I guess the two, I guess there's two parts to that. One is that you want to be able to somehow be able to blindly follow the rules. If nothing else works, you just want to be able to blindly follow the rules so you get to like a very reduced form. But on the other hand, you also want the search, because most problems are hard to search for. You want the search to take risk and try using shortcuts. And essentially, shortcuts in the world of math are theorems, right? Like people have figured out that this particular fact is an important thing to remember, and quite often you can use this as a bridge to get to some other part of the search space very quickly. So, and the idea is that we don't want to do it. I mean, let's say not we, but let's say I don't want to do it exactly the way math does it, where math is a very pure kind of thing. You want to do it much more. I wish I could come up with a system that was a little bit simpler, where we could try, creating a set of rules, creating a set of restrictions to the ultimate rules, creating, let's say, these theorems that will give you shortcuts, without having to be so pure and so well-refined as math. But having a system that lets you do that, I feel like miniKanren is essentially the base of that, but I still haven't quite figured out how to create the right workflow around it. But what you're saying is exactly consistent with what I was thinking about, but I haven't been able to figure out how to actually do it.
Well, one way we could try to approach this would be to look at the Saigas papers, right, and look at the the UPenn paper and see how many of those ideas we can implement, right, and just play around with those, like take one or two ideas from each paper and say, hey, how could we encode this in miniKanren, right, and just see how would we do with that. And that I think would kind of give us more intuition about these things. Let's see. What's the killer app for program synthesis? Oh, the killer app. Well, I mean, I guess the killer app would be to be able to do it at all, right? Because I mean, people have wanted to do automatic programming since the beginning of programming, basically, right? Where you give a specification or you give examples, and then the program just magically writes itself. I can tell you, but I mean, really, no one knows how to do that. They really don't. We're making progress, but it's been slow. I can tell you one example that people really care about that has been getting a lot of attention, and that's Microsoft has been spending a huge amount of effort on program synthesis. So like Sumit Gilwani's group, for example. So one of the cool things that they've been working on has been things like in Excel spreadsheets. Okay, so essentially every non-trivial Excel spreadsheet is just like riddled with errors, right? But so say you want someone to be able to use Excel and to be able to do somewhat complicated formulas, but without having to learn the formula language for Excel, right? The good thing is that when someone's writing an Excel document, they often have lots of examples, and they can say, hey, I want the examples from this column to transform into the examples from this column, right? And because the Excel language is still, most of the things people do in Excel are not super sophisticated from a formula standpoint, and you can actually figure out, you can use this as an example-based synthesis problem and figure out what Excel formulas would let me transform the input from this column into this other column, right? And of course, it could be more complicated because maybe there's a couple of the input-outputs are wrong. They're off a little bit, or they've got some error or something like that, right? So there might be some noise there. But that is something that people really care about. I mean, Microsoft really cares about that. If they can make Excel significantly easier to use, that's a big deal to them. So that's a a restricted domain, but I think that's mainly what you see right now. It's like very restricted domain. And what people call program synthesis, I think, there's really a whole bunch of different techniques. I mean, a compiler in some sense is program synthesis for a very verbose specification. I mean, in Haskell, it's not that verbose. But other things people care about are doing things like synthesizing code, for safety critical things, right? If you wanted to make sure you had a controller for a nuclear power plant or an airplane or something like that, there's some part of that that's really critical, and you want to have a formal specification and automatically generate the code from the formal specification. Okay, so the stuff we were talking about is example based, but there's also a whole branch of formal specification you can create, and we've been able to do a little bit of that in miniKanren. I think that could be pushed a lot further. So what I would see ideally would be a system where you have the relational semantics, like we're encoding right now, where you also have maybe part of a non-trivial program, but part you still want to synthesize, and you have a bunch of input-output examples, and you also have maybe some higher level properties that you want the code to adhere to, and maybe you have a type system on top of that, right? So you have all of these different pieces of information, and what you want is your synthesis system to be able to use all that information in combination. And I think this using in combination is the tricky part, and it's tricky in miniKanren largely because of the way we do conjunction. That sort of one or two of the pieces of information tends to dominate the others. But I think the cool thing about the miniKanren approach is that we at least have a framework or a way to combine different sources of information in a sort of a very natural way. But we have to figure out how to make it efficient to combine that information, right? So you can write a type inferencer in miniKanren. You can write an interpreter in miniKanren to encode the semantics, and you can do the examples in miniKanren. You can put logic variables wherever you want to represent missing code. You can do at least some property-based specification in miniKanren, right? So having something where you can take information from 4 or 5 sources and combine them would be really cool. And like Nahal said, I think the way most of these systems have made progress is that they restrict things. A lot of systems don't have recursion; they only allow folds. Or that UPenn paper, they have recursion, but the recursion is restricted. I think in that paper they have to use structural recursion, where the arguments are always guaranteed to get smaller, things like that. Okay, so you can, as soon as you start layering on these restrictions, you can do much better with your search. So yeah, I think Nahal's right. We have to figure out like what's the right way to kind of combine, or to layer, I guess, on top of the semantics, ways to try to control the size of the search. So it's not that anything goes and we have all of the scheme everywhere. I think the cool thing is with that absento example. The cool thing about the absento example to me isn't that we're removing lambda from the expression, is that the entire system actually still has to use lambda because that's how we're defining append, right? But just in one little place we don't want to have lambda. So in one little place we can restrict the grammar in some way or restrict the system. So that's maybe how I see the miniKanren stuff being used. We want to be able to put restrictions on certain parts of our program or certain parts of our expression to help control the search, but in other parts, we can handle anything. And I think that's like really cool because we can mix this instantiated parts of the program with the non-instantiated parts. We can mix the instantiated parts of the input and output with the non-instantiated. Okay, I've got to show you this one test because I think it's really cool. We just came up with this the other day. No one else has seen this outside of our group. I think it's really neat. So let me show you this. I think it's this one. Yeah, check this out. All right, so let's look at this example. So this is like an append, just like we saw before. Notice that there are two variables, x and y, right? Two query variables. So we have part of the definition of append, and we have this cons thing. Actually, this would benefit from ORCID's optimization. So we got this call to cons, and this should be like car of L. But we have another, so we have two example calls, two appends, and we have another variable in the second call, okay? And we know the outputs from both, but we only know the full input from the first call, and we know part of the input from the second call, right? So what's kind of cool here is that in this one query, we're doing both code synthesis, we're trying to find the missing part of append, but at the same time, we're also running append backwards, right? So like we can express these things at the same time in the same query. And in fact, it's actually quite fast. Yeah, so how long did it take? Actually, I was surprised how fast it was. So, yeah, it's like 147 milliseconds, right? So that's kind of neat. Now, what happens if I reorder these two? Does it take forever? Is it okay? All right. It still is actually pretty fast, 1.2 seconds. And if we do the ORCID trick, sent to lambda in x is the code, okay. Let's see what happens if that reduces the time at all. Yeah, 275 milliseconds. Actually, that's pretty fast. Go back to the original ordering. 65 milliseconds, okay. So, yeah, I kind of like that ordering, actually. So that's actually kind of neat, I think, right? So we have a framework that's expressive enough where we can write down part of the code, but we don't have to write down all the code. We can have, in some places, like an X in this case, a restricted grammar, where X can't have lambda. Obviously, we'd like to be able to control this better, but we've got a little bit of control right now. And we are able to run it backwards, all in the same query, right? And we could, I think we could actually create like an Uber example that had code synthesis and symbolic execution and running forward and running backwards and all sorts of stuff, all in the same query. Like, I think it's the generality of this approach that's so cool. But like Nahal said, that comes at a cost. And I think what that means is that in different parts of the query or different uses of the system, we want to be able to restrict things, right? And we want the flexibility to be able to pick and choose when we want to restrict things. Like, we only want to restrict something about X, not Y here. We can restrict what's going on Y. Actually, we do have a way of restricting what's going on in Y. The way you restrict what's going on in Y is you put a quote in front of Y. And that speeds it up. Yeah. So, yeah, you put a quote in front of it, that speeds it up even more. In fact, we should be able to get it to go quite fast now. Yeah, 40 milliseconds. Yeah, so we have different ways to reduce the search space and reduce our expressiveness. If I remove the quote, now it can actually generate, arbitrary terms, not just lists that are quoted there, right? So, so we have a super general system, and I think the trick is we want to be able to control the generality in like a modular way, or a way where we can have different types of restrictions in different parts of the query or in different queries, right? So yeah, I think something sitting on top, that absento is basically sitting on top of the relational interpreter in some sense. But yeah, like having things like making sure that fold is available, right? Or maybe you want to have fold available but not let rec, right? That's something. We can actually express that right now, but we'd like to make it easier to express, and I think that would go a long way towards. In fact, I think what Michael Ballantyne was doing, I think he actually was using fold to synthesize the append, but we should get him on sometime soon and have him show what he's been doing with the synthesis stuff. But I think that's right. I think you're absolutely right, Nahal. Having tools to better see what's going on with the search would also be good. I guess part of it is I just don't know what the tools should be. I don't know what, it's like I couldn't give someone a specification because I don't know exactly what I want for that. Let's see. Question: have you read Dan Friedman's new book? Or eagerly waiting for it to arrive. I've read parts of that book a long time ago. I haven't seen the latest version, but I was about to order a copy, actually. I think I might just have ordered a copy. Yeah, it just came out like 2 days ago, right? The Little Prover. Theorem proving. So, yeah, I wonder if we could encode the Little Prover inside of miniKanren. Or somehow make them connect. DARPA had a project to infer bits of code based on a huge corpus of examples. Yeah, I mean, that project's like going on now, right? It's like the Muse project. I know people working on it. Sort of like, in fact, that was one of the themes of the program synthesis workshop. There's this thing that they call big code now, just like big data. It's like, GitHub has, I don't know how many millions of repos now. So people want to do serious machine learning on those repositories, and I mean there's like, I guess, billions of lines of Python code on GitHub or whatever, right? So the idea is like maybe you can do all sorts of machine learning and combine that with other sorts of reasoning.
Using change logs to find security issues, maybe.
Yeah. Yeah, or DARPA really cares about things like program repair, right? So where you have like, so DARPA wants to be able to run a program for like 100 years, and in different changing environments where like you swap out the hardware or the operating system or whatever, and libraries that the program uses, and the program sort of like figures out what's going on, and so that can tie into the big data type stuff where it's like, oh, something changed. Let me see if I can find some code that like is kind of similar, right? Using all this information, or like you said, maybe there's a security problem, it needs to do some repair. Maybe it looks at the change logs, and there's all sorts of things that you could potentially do. Obviously, this is like kind of a really messy problem, but machine learning people like lots of data and messy problems, so maybe it'll do well. Yeah, so that's called the Muse project, M-U-S-E. Yeah. Anyway, so that's everything I have to talk about. Obviously, the synthesis stuff. We've been focusing on expressivity, and I think we're getting to the point where we're pretty good with expressivity. I mean, I think we can go a lot further, but now I think the problem is like how do we make it fast enough to actually really be practical? And I think Nahal's actually exactly right. Various forms of restriction or structuring on top. So the type system is a perfect way to look at that, right? You have lambda calculus is very powerful, and in some sense it's too powerful. You can't really reason about it very easily. So you put a type system on top of the lambda calculus, and then you can do reasoning at that level as well, right? And it can make things a lot simpler. And you can put a type system on the lambda calculus that makes all your programs terminate, right? And that gives you really strong guarantees. So yeah, I think so there are all sorts of heuristics we could also use, right? So for example, when writing a recursive function, it's actually very unusual for most of the cases of a recursive call or of a recursive definition. Okay, I'll put it a different way. Generally, when you're writing a recursive definition in Scheme, at least some of the cases, including usually the first cases, do not involve recursion at all. Okay, and then with the later cases, it's actually relatively unusual to have multiple recursive calls in all of those recursive cases. So there's just like a whole bunch of things that are sort of they're kind of like probabilistic or heuristic type things, right? So I think we can, another thing we could do is try doing stuff with like A-star search and actually having heuristics to guide the synthesis. I mean, I think I think it's actually not that hard, probably, to encode a lot of those heuristics. There are only a few of them, and they're fairly straightforward. And then, of course, there's all the machine learning or the probabilistic inference stuff. So, Oh yeah. So I don't think did. I show you all the Did I show you all the recursive neural net stuff that I had trained on the scheme code? No. Actually, so I've been working on this with my friend Anita, and Michael Ballantyne also, was one who pointed me to this blog post on. There's a blog post called there's that famous article, The Unreasonable Effectiveness of Mathematics, and this is the blog post, The Unreasonable Effectiveness of Recurrent Neural Networks. Have you seen this blog post? So it's about these recurrent neural networks, which is a type of deep learning, which is like all the rage now. But the cool thing is that these recurrent neural networks, they work well when you give them lots of data, and they can generate text. They can spit text out. So I was thinking, well, I've got 1 million miniKanren programs that evaluate to I love you, right? So what would happen? I mean, not 1 million miniKanren programs, 1 million scheme programs generated by miniKanren, right? So what would happen if you fed these 1 million programs into the recursive neural net? Like, would it be able to generate code? It just generates a string of text, sort of probabilistically, right? Would it be able to generate things that look like I love you? And the answer is yes. But I think it probably overtrained, because it looks like most of the answers are actually in the original source. So need to play with that a little bit. Maybe Nahal actually has some ideas. I don't know if you play around with recurrent neural nets, Nahal. So Anita and I want to play around with that some more. But we've actually, we were able to train it, and it generates the text quite well. So let's see if we can find this blog post. It's a really fun blog post. It's really neat. Here we go. This is a really cool blog post. I really like it. Let me bring up screen share. Yeah, there we go. So this gives lots of examples. It gives some high-level description of what a recurrent neural network is, and it shows examples of them in use and all that kind of thing. But then it's got a bunch of cool examples where you're training on things like Shakespeare, and then it generates Shakespeare, stuff like that. So it's like this is like fake Shakespeare that the recurrent neural network generated, right? So it actually knows that you have a speaker, and the speaker's name's in caps, and it has a colon. Like, it actually learned. I mean, it didn't know any of this stuff. It was like completely trained. It didn't know English, right? It was just trained from scratch. So here's like an example where it learns from Wikipedia, and it can generate Wikipedia pages that are made up with links that are made up and stuff like that, and it can even figure out like kind of fake URLs, and it can figure out like the markup and all that. It can generate random valid XML, and it can even generate like LaTeX. So they trained it on the algebraic geometry textbook, and it started generating this nonsense, but actually like looks okay. Hallucinated algebraic geometry is what they call it. Yeah, so you get all this sort of stuff out. And they even trained it on Linux source code. And so this is fake Linux source code C that you're getting out. So anyway, this is like a really cool blog post, and all the source code is online. And it's actually really easy to install these tools and get it going. So I think this is a fun blog post to look at. It doesn't solve all the world's problems, obviously, but it's I don't know. It's exciting to play with these things. I find it important to find shiny things that I really get excited by. So what I do is Anita and I started playing around with that stuff and I generated I fed it in the million I Love You programs in Scheme that were generated by miniKanren, and then I asked it to start generating programs. Let me see if I can find this real quick. I'd forgotten about that, but it's really fun. Okay. Here we go. Yeah. Share this. Yeah, so there's this car RNN repo that's available that's tied to that blog post. And, basically there's some Ruby tool, or sorry, not Ruby, Lua tools that you can get for recurrent neural networks, which are quite nice. And let's see, data. Okay, so the data, it comes with the data from the blog post. And one of the other pieces of data I gave it was this 99,000 ways to say I love you, right? So here are all these programs that I generated from miniKanren that evaluate to I love you in Scheme. So that's what I trained a recurrent neural network on. Yeah, so this is the data that I got out from training it. And yeah, I also trained on Quines, by the way. It didn't do quite as well in the Quines. Maybe I can actually show it running. I'm trying to remember how. Yeah, so this is the Quine stuff. Yeah, I think I can just run it now. All right, let me see if. Yeah, let me bring up my generator thing. I think I can. Hold on 1 second. Let me see if I can get this working. Anyway, it's really fun to play around with. I strongly encourage anyone to, who's at all interested in things like neural nets, play around with it. It's a very accessible blog post. You don't really have to understand how it's working to play around with it, but if you want to, then there are lots of resources. I don't really understand what's going on, but I understand enough to kind of get in trouble, which is cool. So let's see. Okay, here we go. So the code on GitHub, I'll also put links to this online. It's right here. Igor asks, is it possible to mix sources like a Markov chain? That I don't know. I'm not, I don't know enough about it. I know that there's a lot of interest in trying to combine these models in different ways. I suspect that people have played with it at least. I'm not sure if this tool lets you do that. Okay, so here we go. So now we've done training. I'm going to sample. Okay, so let's see if I can sample. Yeah, I got it working. Okay, let me check this out. That's cool. That's cool. All right. All right, can everyone see that? Okay, cool. All right. So I've trained it already, and here's I'm going to just run the Lua tool, and it's just going to probabilistically generate some text. And this was trained on, like I said, on the Million I Love You program. So let's see what it comes up with. Oh wait, maybe this is the Quine one. This looks like the Quine. Yeah, this must be the Quine example. Yeah, this is definitely Quines. Because if you look at how the Quine works, right? You've got like quote of quote, and you're taking cars and could or like you're building up lists, and you have this lambda on the outside. So yeah, so this is actually trying to generate code that it thinks looks like a Quine in scheme. And it's not quite getting it right. So, I mean, not only aren't these Quines, but sometimes it just does things that like kind of aren't right, like that. That's kind of goofy. And then it'll just kind of randomly make mistakes. Let's see, generate some more. Oh, okay. So this is the same thing because I have to give it like a seed or something. I guess it's always it's deterministically generating the same sequence in the beginning. And you can also say how much you want to give it, like how much text you want to give it. Let's see, is there like a help or something? Yeah, so a seed. So you can give it a seed. I can change the seed and get back different text. Okay. And what else? Temperature. Oh. Maybe I should play around with the temperature in that other one. But anyway, you can also, yeah, you can prime text. You can give it part of a text, like part of the text, and it will like finish generating the rest of it based on what it thinks is correct. You can do all sorts of fun stuff with it. But yeah, so you just train it on basically a text file representing the things you care about. It trains a recurrent neural network. You can say how big you want it to be. If you have enough data, you might want to run it on GPU. You might even want to run it overnight or over a couple of days, and then you end up with this model that you can sample and generate text. So this system knew nothing about scheme, nothing about Quines, any of that stuff, and yet it's like generating for the most part legal scheme code. They're not necessarily Quines, but it's generating legal code. And let me see if I can. See if I can find the example for the Million I Love You programs. Maybe that's the only one I got. Yeah. Yeah, I guess I had to train. Oh, I think Anita had the Million I Love You ones. I think she trained on her computer because it took. She ran that like over a day or two, I think. So those are maybe, I think the I Love You programs are maybe overtrained because they had so much data. They ended up essentially spitting out a lot of the programs that we saw before. I mean, some of them are like small variants of it, but these Quine programs obviously aren't really Quines, but a lot of them actually run in Scheme and do something. So I thought that was cool, and they're actually, this is trained on 1,000 Quines, not that many. So it'd be interesting to see what happened. Generally, the more data you give these systems, the better they do. So if you gave it 10,000 quines, it'd probably do a lot better. But you could see that it's already learned kind of what scheme looks like, right? And kind of what a quine looks like. So I thought that was pretty cool. So some combination of probabilistic inference and neural nets and miniKanren, seems like that would be fun. Can you combine this somehow to try to bias miniKanren search? Michael Valentine was hoping that somehow you could train this neural network and then use the neural network to kind of guide miniKanren search for certain types of things like quines. Interesting idea, I'm not sure. All right, Nahal, did you want to talk about Julia at all?
I can. I think I can also just answer questions if you have them as well. Let's see, how does this work?
Yeah, I kind of have.
Okay. All right, so I have the snippet that we talked about a long time ago, and I could just refresh your memory on that. But I think you're also mentioning just some of the stuff that you're interested in, and if you had specific questions, I could do that as well.
Well, I guess the main thing I was interested in was whether or not you could use the staged evaluation that Julia supports to do things like reorder miniKanren goals at runtime, things like that. The things that we want to do to try to better take advantage of information in a query, like based on groundness and stuff like that. Like so for example, when you call the interpreter the you have the input expression and output value. If the output value is ground, the input expression isn't. You want the ordering of the goals in the interpreter definition to be different.
So I guess I'll just try to give you the practical answer, which is one thing that's nice about Julia is it tries to keep the AST around of all the definitions that you make. So basically, if you can grab the AST of either a closure or a named function, or whatever, you can start doing those kinds of things that you just mentioned. It's a little bit unfortunate that they don't preserve the original AST as it was entered into the interpreter or into the compiler. They preserve what's called the lowered AST, which it basically just applies a bunch of removes a bunch of syntactic sugar, but it makes it a little bit harder to realize, okay, this is a specific goal, and I want to reorder it up. It's not impossible, but you have to kind of know a little bit about the details of what's the difference between the expression that you put in versus the lowered AST that actually gets saved. So this is like some sort of detail about Julia, which is probably not that interesting to most people, but unfortunately that's the reality, that it's not quite as easy to do the kinds of things that you're talking about as I would like. But it's still possible. And I still feel like it's the only language that at least tries to keep the AST around.
Okay, so the challenge I have is related to cons in the relational interpreter, right? Let me share my screen real quick. So sort of the canonical example of this I have is in the definition of cons. Oh, well, I guess this one doesn't show it. Okay. In the definition of cons, you've got an expression coming in, an environment, and a value. And a cons expression looks like you're consing, it's probably more like E1 onto E2. And you get back pair of V1, V2. That's the way I think about it. But you have to make a call first. You have to decide to either evaluate E1 first or V2 first, or E2 first, and you get back V1, V2. So the idea here, these things are stupid. Okay. That's how the code should look. So the idea here is that you have to decide if you're going to evaluate E1 first or E2 first, right? And this matters because if I tell you the expression is cons E on the 5 and the output is some V I don't care about in 6, okay, that's one example. The other example uses the other ordering. Okay, so if you evaluate E1 first and then E2, then this first call, or this first call to evaluate, like is going to be essentially evaluate of this is the input expression, and this is the output value we expect. If cons evaluates this arguments left to right, evaluate immediately detects that this is inconsistent information. 5 and 6 can never be made the same. Doesn't matter what E and V are, just fail. Yet, if you change the example slightly, so it's using the same values, but the order of the arguments is swapped. So you have this case where E1 is evaluated first. There are there are infinitely many expressions and values that could be generated in Scheme. So even though this is still inconsistent, if you evaluate from left to right in the arguments, what miniKanren will do is pick an expression E, evaluate it, get a value V, and then try to evaluate 5, get back 5, and that's inconsistent with 6, and it'll fail, and it'll basically backtrack into this E and generate another expression E. So this will go in an infinite loop. So this one fails immediately in like a millisecond, and this one goes in an infinite loop and loops forever. So in cons, this is a very simple example. If when you're evaluating cons, the order of these two evaluations is critical. If you know that E2 is ground and E1 isn't, if you know, like, say, E2 and V2 are ground and E1 and V1 are not, you absolutely want to evaluate in this order rather than the standard order. So, that's the sort of thing that I'm hoping could be done at runtime, and maybe Julia would be able to detect. Maybe you could write some Julia macros or do some staged evaluation and do some kind of dynamic code reordering at runtime based on the groundness of arguments.
Yeah, so for that simple example, I could think of a way where, so ignore all the stuff I was talking about ASTs for a second. There's a way just to use Julia's, what do they call it, multiple dispatch to solve that specific problem, right? So it's a little bit tedious, but so basically you would have one version of, so in that cons expression, let's say there's sort of 5 relations in your con D there. Your screen's not visible again.
Yeah, let me bring it up again real quick.
Right. So you can imagine taking the first 3 expressions and grouping them into kind of a sub-relation, and the last 2 and grouping them into. We don't have to do it in real time, but just sort of conceptually, take the first three and put them into one subrelation, and put the bottom two into another subrelation. And in Julia, the way you do that is you do it the same way you do it in Scheme, but then you can create a version of sub-expression A which has type information. So you have one version which has sort of no type information, just like Scheme, and then you could create a second one that has annotations for types of some of the inputs. Basically whatever a ground expression would be, and so there'd be sort of one version when the first argument is ground, and another one when the second argument is ground, and the compiler is pretty good. It kind of knows how to generate code that quickly tests which of those three versions to call. So it's pretty good, and a lot of math code needs that kind of stuff. So to a certain extent, you can do what you are asking for. And in fact, when I wrote my miniKanren, microKanren implementation in Julia, I used that kind of multiple dispatch stuff all the time.
Can you show an example of that?
Okay. Yeah, sure. Let's see, where did it go? By the way, I have only until 6 o'clock. So 7 more minutes, so I might run out of time. But let me just try to show you something. Let's see. So here's. Can you guys see my screen actually? Let me just make sure. Oh.
I can see it at least.
Okay. So this is just this is actually not where I was using it, but this is just an example to explain how multiple dispatch works in general. Right. So there's a silly function. Doesn't matter why it's named this. It's called got_some_vars, and it takes two variables. And sort of the untyped version just returns nope. But if the second version of the same function, if both of the parameters are of type .var, then it says yes. And if the first one is a var and the second one isn't, this is sort of kinda. And then here you can use a trick that's actually used a lot in Julia, where you write the symmetric case by kind of just flipping the parameters and calling back to this case. So the compiler takes these four things and generates relatively efficient code. So that's actually probably the key innovation to Julia, is how this works, where in general you write untyped code and then you can specify types for special cases. And you can imagine, like in matrix libraries, where you might have a generic expression for how to compute an eigenvalue, but then if you have a symmetric matrix, you do it a different way. If you have a sparse matrix, you do it a different way. So it kind of makes organizing your code relatively simple, in particular where in object-oriented programming, kind of the first variable is a thing that you can dispatch on. Here you can dispatch on sort of both or any of the arguments into your function. Does that make sense?
It does. That's really cool. And that reminds me a lot of how Mercury works.
Yeah, it's a little bit like how Mercury works, but here's the place where I actually used it in my implementation. So I have Unify, and this version, I actually don't call it Unify, I call it Unify left, because this version of Unify, I forget why I call it Unify left. There's some reason, but basically, in general, if it doesn't know anything else, it tries to see if these things are kind of bitwise equivalent. But if it knows that one of these things is a variable, then it does, try to extend the environment. Well, it does, does what it's supposed to do, and then, it only handles the left case. And there's some place where I handle the right case. It was something I tried to be clever. I forgot what exactly I was doing, so I can't explain it right now. But here's a place where you're using multiple dispatch and the same thing you can see like in walk, there's the base case where you do something simple, but if one of the values is a variable, then you can do something more complicated. So that's at the low-level implementation, but I feel like when you're modeling relations, like your cons, for instance, in your relational interpreter, you might be able to do exactly the same sort of stuff.
Yeah. Would it be hard to build a regular miniKanren on top of this using the macros?
So it wouldn't be hard to do it if we didn't. Well, so we could probably do it with S expressions. There's actually a partial library that's not that bad in Julia that would be able to handle that. Or we could do something without that library, which is create essentially a miniKanren, but instead of using S expressions for the programming language, we'd use essentially Julia syntax because it's homo-iconic in its own way. So we could just use its language to create a kind of mini Julia, if you will, like a kind of dumbed down version of Julia that doesn't have all the features, and write an interpreter for that. The only
That
thing
would be awesome.
I haven't gotten around to, just like for whatever reasons, I never got around to putting in absento and disequality. So that's like a prerequisite to do any of this. It's just like there's two kind of critical things missing from my implementation. I just never got around to doing. But I don't think either one of those would be hard. We just do it, and then it's pretty straightforward to do the interpreter after that.
That'd be really cool because all of the interpreters that I know of for miniKanren, and correct me if I'm wrong, David and Orchid, all the ones I've seen have been for like an S expression based language. So it'd be really neat to see us interpret a language that's not. And it might be more accessible. I think, giving demos and stuff like that.
It would be a lot more. I don't know if it would be a lot more accessible, but it would be accessible to a different group of people.
Exactly.
Julia is actually the language where it's the only language that I know of that it would be relatively easy. Maybe ML or some of the other ones like the ML that. Oh gosh, I'm forgetting his name, but you're a co-author on the book.
Oleg?
Oleg, yeah, he uses a kind of templated version of ML where it might actually work well in that instance as well. But otherwise, Julia, because it's very macro friendly and it uses its own syntax for the macros, like it would not be that bad. So that's something that we could try to get together at some point if you have time this summer. We could try hacking it.
Yeah, that'd be awesome. I get the sense that wouldn't be that much work.
No, we basically do three things. We'd put in disequality, absento, and then just like you start initially with a lambda calculus interpreter before you do a full scheme interpreter.
Yeah.
We do something like that, where we just do like a very simple version of Julia that doesn't have all the bells and whistles, but just like a Turing complete version of Julia, and then you just build from there.
Yeah, I'm down for that. That'd be really awesome.
Unfortunately, I've run out of time, so I need to head out. But just thank you. I guess we won't be talking. We won't do the Hangouts for several weeks. So just bye to everybody. Looking forward to picking up. I guess in August.
Yeah, looking forward to seeing it, and looking forward to hacking on the Julia version.
Yeah, I think that's actually a doable project. So when you have time, you just send me an email. We can try working it out.
Great.
All right, take care, guys.
All right, thanks, Nahal.
Bye.
All right. Well, Nahal's gone. Igor's gone. We're 3 hours in. We had our troll of the day. Need eye bleach for that. Yeah. So anyway, is there anything else anyone want to talk about, or are we good? How's it going, Raja?
Hello?
Hello, how's it going?
Can you hear me?
I can.
Okay. Let's see. Yeah, I had a couple questions just about, I think it was general scheme stuff. Here,
Sure.
let me see if I can share my screen. So I've been working with Racket, the miniKanren version of Racket, and I think the last time I was on, I had something with patterns. Um, I don't know what you can see. Maybe I should resize this.
Okay. I
Maybe
can see it now.
Let me try this. Okay, pretty much I just wanted to just mess around with miniKanren and use the Racket drawing library, the How to Design Programs image library, just to do some, fun stuff to get miniKanren to automatically draw pictures for me.
That sounds cool. All right. So let's. What do you got?
Well, the first issue that I came with is that I didn't like doing all these condes all the time. So pretty much I'm giving a range is saying, okay, it can either have, I'm drawing polygons and they can have 3, 4, 5, 6 sides, but I'd rather define a macro that just does it for me. And I guess my macro programming skills maybe aren't up to speed, but I was trying different ways of just automatically creating condes so that I could, let's see, where did I put it? Yeah, so that I could just do something like this or something like this.
Okay. So let's see. You
This would
want
be, here,
like
let me
let's look up a red, green, blue one, for example. So you're enumerating the values you want to be able to unify against. Is that right?
yeah, so this right here is what I want to create out of a macro. So this is what I want to do. I want to say define condes, and then here's the range. So this is what it would look like if it succeeded. I just found that putting loops inside of macros or trying to eval, like I was trying to apply cond E inside of a macro and it wouldn't let me. So I just didn't know if you had a solution for that.
Well, why don't we write a macro?
Okay. Anyways, I was just gonna. I guess I can just show you without the macro how it all works.
Okay.
I'll run it. I believe.
Orchid was wondering if your code's online, by the way.
Oh no! I just kind of hacked this together while you were talking. So.
Oh, cool.
So,
Well, too bad Nahal's not here to see this. He loves the geometric stuff. That looks really nice.
So anyways, it just starts off with radius O, which means it's going to be either 5, 10, 15, 20. It's going to be 3, 5, 6, 7, 8 sides, and then actually I'm not using this. And it's going to be green, so I could add stuff to this. But the cool thing is that you can start putting a lot of different transformations. I was trying to see if I could put all of the operations from the drawing program into it, and then make like a random miniKanren that just randomly creates images. And then I could say, hey, I like that one. How did you find that? And then maybe some heuristics to, I don't know. It's not that I want to draw images, it's just that I think this is a cool way with Racket how you can put images into the to the interpreter, that it just makes it a little easier and more entertaining for me to hack around with miniKanren, you know.
So this, I think, this feels like this is getting back to what you were talking about before, where you want to be able to select kind of things you're interested in and tell miniKanren, hey, find more of these, or bias the search towards these things, or whatever. Is that sort of similar idea?
Yeah, this is more of just tinkering around, but it's I want to just get more into how it all works. So I thought this was kind of cool. But I would really like to just be able to easily define like a range of condes and not have to do this, you know.
Sure.
If
So
you know how to
Orchid's
write the
got,
macro.
yeah. In fact, I don't even think you need a macro, to be honest. I think
Really?
you probably don't need a macro. But let's see what Orchid's got. Maybe you could do something like this inside the macro cond.generate list of clauses. Yeah, that's a good point. Yeah, so the thing is, you can just write a little a little function that takes so your range is going to return a list of values, right? So
Yeah.
basically, you want to be able to take a list of values and have an argument that you take, and then have a cond where each clause unifies that variable with one of the values in the list. Is that correct?
Mm-hmm.
Okay. Well, I think we can write that just as a regular function. So let's Well,
the problem is that conde's syntax is a little strange. Like this, I was trying to put a list of these in, and I didn't know how to unlist it in the cond. That's why I thought I needed a macro.
Yeah, I think we can write it just in standard miniKanren without a problem. I think.
Okay.
I could be wrong, but let's try writing it and see if it does what you want. Okay.
Cool.
Okay. So yeah, can you bring up the REPL or whatever?
Oh.
Or yeah. Okay. So can you just type range 38 just to make sure we? So that should give us a list back, right? Yeah. Cool. Okay. So let's just define a function, and we'll call it, I don't know, try all or something like that.
Okay.
Try all.
Oh, trial O.
Or try all, try hyphen all.
Try all.
Yeah. Try all O, I don't know, whatever you
Okay.
want to call it. And it's going to take a list. Or so it's going to take X and it's going to take a list. Okay, so X will be the variable, right? All right?
Mm.
Okay. Now, so this is going to give us a goal back, right? So one thing we could do here is we can do like a fresh nil. That's always a safe thing to do when defining a function.
Like this?
Because
Or
sorry, a fresh empty list. Yeah. So I always put a fresh there. No quote. Just like fresh empty parent
okay.
just means it's a
Gotcha.
fresh form and we're not introducing any variables. Right?
Just in case you want to throw some variables in there.
Either that, or just in case we want to have more than one clause. It's like a very easy mistake to make when writing these sorts of functions is that if you inside the beginning of every definition or between any lambda is an implicit begin, so it tries all the expressions in the body, evaluates them all for effect, and then evaluates the last expression and returns its value. But basically what that means is if you had two conds inside of this define, right,
Mm-hmm.
and they weren't wrapped in a fresh, the first cond would be essentially ignored, and you wouldn't understand why your program doesn't work.
Yeah.
So if you put a fresh, then it's fine. You can have as many of these things as you want.
Okay.
Okay. So let's do a condy. And this condy is going to have two clauses. And in the first clause, we're going to check to see if the list is empty. So how do we check that? So we could do that if we were just using scheme lists. And for what you're doing is probably fine. But we want this to be as general as possible and to run backwards. At least I always want to make it run backwards. So I would, instead of doing a null chest, I would do an equal of LST to the empty list. And that way it'll work even if the list passed in is a fresh logic variable. So if you do an equal quote empty list to LST, that will work if list is bound to a list. It'll also work if list is a logic variable. Okay?
Oh, okay.
Okay. And if that's the case, if we have the empty list, well, in that case, do we actually want to do anything, or we just want to fail?
I'm actually, I don't know. I never thought about doing this in miniKanren itself. So,
So actually, I think, okay, so your definition is interesting because once we get down to the empty list, we actually want to fail, right? Like we don't want to produce any values once we've grabbed everything from the list. So this is a little unusual in that sense. So we actually don't need, I take it back, we don't need the empty list, but you can keep that test because we're going to modify it slightly. Okay, underneath that fresh nil, let's add another thing before the condy. Okay, we're going to add a call to equal before the condy call. And we're going to add to the fresh, let's add A and D as variables. Add A and D. Okay, and we're going to unify LST with a cons pair containing A and D.
With that, okay.
So we're going to cons A to D, like call the cons A D, and unify that with LST. So this means that we actually have a non-empty list, okay?
Oops.
Okay. And now, if that's the case, so
So
we're
we just
going to
see if a D is null or equals.
Well, okay, so we actually don't have to check the null test because we're going to fail in the base case. What we can do is we can have one condy clause that takes the first thing in the list, which is A, right? And we're going to unify A with X. So say list is the list 3, 4, 5. Then in this case we would be unifying 3 with X. Okay, so that will succeed, and X will be bound to 3 in that case, right?
Mm-hmm.
Okay. But now we need a recursive case also. So we're going to have another clause. And in this clause, what do you think we're going to return or do?
Try all the cutter of the list.
Exactly.
And let's see, D is the cutter, right?
That's right. Mm-hmm. Exactly. That's right. And then you should be able to close it all off. Okay. And let's try doing, do you have miniKanren loaded? Do you have run loaded?
Yeah.
Okay. So yeah, good. Okay, so we should be able to do a run, like a run star of Q
Mm-hmm.
in parens, I think.
That's right, of course.
And then a trial O of Q and range, 3, 8 or whatever you have.
Oops.
There you go. So it gave you back 5 different answers.
So yeah, so I can rewrite these now. Okay, that's okay.
Yeah.
That's cool. So now that I didn't really think about doing it in miniKanren. I was just trying to just eval.
You wanted to generate miniKanren code. Yeah, and you could do that too. You could generate a condy as well. Okay, you could totally do that.
Now, just for my own knowledge, how hard would it be to actually write that macro?
If you already have the list, it's pretty simple. Shall we write it?
It's just because this is where I get into trouble right here.
Yeah, you don't want to. Okay, I see what. Okay,
this is probably ugly what I'm trying to do.
Let's see. So what is val? So val is an expression that's going to be.
No, so this is how it should work. It should be val would be the range.
Okay. Well, okay. So if you're going to do you're doing syntax case. I see. Yeah. So I think what you would want to do is you would evaluate that expression, right? So you've got this expression range 5, whatever. You want to evaluate that in the macro to get the list.
Mm-hmm.
And then you're going to basically for each element of the list, you're gonna create.
I just can't unquote. I can't unquote something inside of a macro, and it's probably just my own lack of understanding.
Yeah.
how that works.
So what you're gonna do is you're just gonna generate a Conde expression where it has a Conde clause for each element in the list, basically.
Yeah, and I believe I've done that. Let's see. Somewhere. Oh yeah, build condes. I think this is it right here. Oops. So if I do this, I can make a string of it.
Oh,
but
I see what you're trying to do. Yeah.
Evaluating it is inside of a macro is the part I just don't get.
Oh, well, the other thing. Okay. Okay. So can you go back up to your build condes list?
Okay.
That definition.
You resize this.
So let's change that definition slightly. After that comma before a map, can you put an @ sign, an ampersand? I'm an @ map.
Mm-hmm.
Yeah. Try running that. Try putting that definition in and running it again, please.
Okay. No, I saw this. Now, what's the ampersand again?
So if you notice, your Conde ended up with an extra set. The Conde clauses ended up with an extra set of friends wrapped around them.
Oh, that's how you get rid of those.
Yeah. This is called a comma splicing form. This is
yeah.
Yeah. It's like you basically need that when you're doing things like map. Okay. Yeah. Unquote splicing is like the technical term.
Okay.
Okay. Now that is an expression you can actually evaluate because the other one was actually syntactically incorrect for Conde.
Inside of the macro?
Well, okay. So what you really want to do, if you want to write macros, then you want to do something that's metaphorically like this, okay? But the code you generate at the end is going to, you need to make sure that your macro turns it basically into a syntax object, which is how it works in syntax case.
Well,
so
maybe just point me in a place where I could just read something. I don't want to take up all your time.
Sure. Yeah, I can point you for. We can also do a very simple macro. If you already had the list. Thanks, Eric. See you later. There's also a way if you already have explicitly the list, you can easily write a macro. But I think for what you want to do, you really do probably want to have syntax case. So yeah, I can point you to something. If you can email me with a reminder, I will send you some links to some material and those sorts of things. Okay. And yeah, this is actually a pretty short macro to write. I don't think it'd be very long at all.
I know it's not.
Sure. The only interesting thing, in a sense, is that you want to be able to put an arbitrary expression, so you don't know the length yet of the list at runtime. So yeah. But if you already had a list, say you actually put in, like sometimes you're calling it with an explicit list, right? Like 3, 4, 5.
Mm-hmm.
It's very easy to write a syntax rules macro that would take that list and then generate the Conde code. That's very easy. In fact, we can write that right now. That's like a really short macro. It'll just take a minute.
Okay. Am I writing it?
Yep.
Okay.
Okay. So let's define a macro. It's called so define syntax. And let's call it, I don't know, Conde list or something. So no parens for this one. Yeah. And then hit return, syntax rules, and then set of empty parens, and then hit return, a square left paren, and a square left, sorry, a regular left paren, and then underscore, which stands for the macro name, cond list, and a space. And we're going to just take an explicit list. Actually, you want an X also, right? You want an X and an LS. So let's do an X and LS. And we're going to assume that LS is actually bound. Okay, that's already like a list, not a call. It's like an explicit list. It's like quoted or something. Okay. And actually, let's change that LS to be the empty list. No quote though. And in this case, we're going to return. Actually, you don't want it. Let's see. Now we should just be able to like map over it.
This is something that I thought was going to be super simple, and then it just turned into, so anyways, I can buy. This is the kind of that @ sign is what I was kind of dealing with before. I think I can figure this out now. So
Okay.
I'll put more research into it.
You should be able to do that with syntax case really easily, I think. So,
yeah, and I know this is miniKanren, not scheme, so.
Well,
I
think writing a scheme macro for miniKanren is definitely in scope. But yeah, why don't you with the comma @ thing, and also knowing now that you don't even have to use a macro, right?
Yeah, and that's what I'm going to do now is just throw that into the run with everything.
Yeah,
so
okay, let's get rid of that macro, but you should be able to now replace those uses, right? Those hand-coded things.
But I think because if you go to the documentation in Racket for how to design programs /image, there's a lot of image transformations and fractal types of operations. So I think if I put all of those operations in, and then had miniKanren just start using them at random, who knows what kind of cool images it could come up with.
Yeah, and it'd also be neat if you could give it an image and have it figure out what the transformations were.
I don't know if it stores the actual lines. I think it's just bitmaps. So you'd have to get it to analyze the actual bitmap itself and try to figure out what it is. But I guess you could do that.
Well, I guess one thing you could do is maybe look at the source code. I wonder, do you know if it turns it into a bitmap before it does the transformations, or is it at the end? If it does a bunch of symbolic transformations and then at the end turns it to a bitmap, you might be able to do something like that.
Well, I haven't been able to actually work with the actual lines and things. It's pretty much, I think, just an image bitmap thing. Once you call like regular polygon or something, it actually draws that straight to it. You don't get to keep the line information and the points and the colors and everything.
Okay.
But you could probably find an SVG library or something that does that.
Well, another language that kind of does stuff like this is PostScript, which has Forth built into it.
Yeah. I was more into trying to create, because I wanted to create like a random miniKanren that would swap in between the there's that one line that once you change it, it totally changes the whole ordering of how miniKanren works.
Oh yeah. Mm-hmm.
Yeah. If you just randomize that, then it would traverse the tree in who knows what types of ways. That's more of what I was trying to do, just
Sure.
having miniKanren come up with something random, and then maybe after that find out how to get there easier. Once I
Alright,
figure
cool.
out what is interesting. But that was it.
Yeah. Well, that's really neat. Yeah. Well, now you know how to write that function. You can write directly just in Scheme and miniKanren.
Cool. Yeah, that'll work.
Excellent. Well, thanks for showing that. That's really cool. All right. I think we're losing the audience now, which is fine. We've gone on for like 3.5 hours now. So anyway, well, thank you for joining us. Sorry about the troll. I don't know. I have to figure out some better anti-troll technology. But thank you, and thanks, Orchid, as always, for joining. And I guess it'll be like 5 weeks till the next hangout, unless people want to hold a hangout on your own. But thanks, and I think I'll go off air, and if anyone wants to talk afterwards, that's cool. Otherwise, I'll see you all in just over a month. Bye.